So I've been thinking about this possibility and planning for this possibility of finding electromagnetic counterparts from gravitational wave sources for about a decade now. And when this alert came in from the gravitational wave observatories telling us that they found the first collision of two neutron star binaries, it was of course an astounding moment, something that I and others have been waiting for many years. And we were ready for it. We had all of our telescope observations planned, and we executed those as quickly as we could within hours of getting the alert for the collision of these two neutron stars. And looking at those first images and seeing the light, the visible light from this neutron star collision was really a transformative moment. We were looking at a galaxy where there was nothing there before, and suddenly we saw this bright source of light. It was kind of X marks the spot for finding a treasure in the sky. Binaries composed of two neutron stars, which will eventually collide and produce a burst of gravitational waves, start their lives as two massive stars. Each one explodes as a supernova and leaves behind a neutron star. And those two neutron stars orbit each other for billions of years, getting closer and closer because of the emission of gravitational waves, until eventually they collide into each other and produce this very large burst of gravitational waves. That is what the LIGO and Virgo detectors saw and announced to us. We started observing that region of the sky using an instrument called the Dark Energy Camera on the 4-meter telescope at the Cerro Tololo Inter-American Observatory in Chile. And we use that instrument because it can cover a very large area of the sky very rapidly. And in those series of images, which we then compare to observations of that part of the sky that were taken several years earlier, we found a completely new source that wasn't there before. We could just see it right next to a galaxy. It was kind of screaming at us, kind of like in a treasure hunt. And that was the first moment where we understood that there was an electromagnetic counterpart in visible light to this gravitational wave source. So as soon as we discovered the visible light counterpart of the neutron star binary collision, we of course continued to study it for several days and weeks, taking pictures every single night with a dark energy camera and the Gemini telescope. And what we found is that over time, the source declined in brightness. It started very bright, very obvious, and over the course of a few days and about 2 weeks, it essentially disappeared from view and will never be seen again. So we have used a large number of telescopes in studying the aftermath of this gravitational wave event. One of those telescopes is SOAR, which allowed us to dissect the light, the visible light, from this electromagnetic counterpart and study in detail the composition of the material starting only about a day after the event happened. By using the Gemini Observatory, we obtained spectra of the source. And that showed us directly the evidence for heavy elements being produced in this neutron star collision. There's been a long-standing mystery in astronomy of where the heaviest elements in the periodic table actually come from. And of course, one of the most famous of these elements is gold. And here, for the first time through our observations, we show that these heavy elements, including gold, actually come from these catastrophic collisions of two neutron stars. Which is something quite astounding. I think that when we all look down at our wedding band or a necklace around our neck, we should think that that gold came from this catastrophic collision of two of these incredibly dense neutron stars. So one of the particularly exciting aspects of studying the collisions of neutron stars in both gravitational waves and electromagnetic radiation is that it gives us a completely new way of measuring the Hubble constant, which is the measurement of how fast the universe is expanding. We can measure the distance to the object from the gravitational wave signal, and we can then measure the amount of redshifting, which tells us how fast the universe is expanding, from the electromagnetic signal. And by combining these two measurements, we can directly measure the Hubble constant. So I've been studying explosions in the sky for almost 2 decades now, and this is by far the most exciting scientific discovery that I've been involved with. And to actually see this potential and this dream realized is really astounding. And it is something that I suspect that I will remember for the rest of my life and the rest of my scientific career.